Hi, Sam. Today, the point of this talk is to go over a project that I will be developing for use in my internal medicine year. This project will center around image processing. Specifically, I want to look at usual interstitial pneumonia. I want to see if I can develop a machine learning model, an artificial intelligence model, an image processing model that is able to look at various high resolution CT scans and then identify usual interstitial pneumonia, probable interstitial pneumonia, as well as indeterminate for usual interstitial pneumonia. I want to see if I'm able to categorize these with the same degree or lesser degree of accuracy that a radiologist would have. In the whole pipeline of usual interstitial pneumonia, this would add this would be in the multidisciplinary discussion section where a lot of experts, surgeons, pathologists, pulmonologists come together to determine if the individual has usual interstitial pneumonia. So, how do I go about building these skills? I'm a skilled programmer, skilled in medicine as well. However, this is still a new project. So, one of the first things to do is to just break up the process into different components. The first being learning what usual interstitial pneumonia is, the second being learning how to develop image processing to apply that on various data sets, and then eventually tying everything together by using the image processing techniques that I learned with the guidelines that I've learned, and then coming up with the project and seeing the results. So, the first thing to do is to learn about usual interstitial pneumonia. And for me, this video is really good. Usual interstitial pneumonia. I found some Mount Sinai videos too on interstitial lung disease. And I found a George Washington University video that talked about interstitial lung disease for the general internist. One of the main things I found for the radiographic side of things that will definitely be useful for the project is the American Journal of Respiratory and Critical Care Medicine's guidelines for 2018. So, on first look, even through watching this video, it can be very difficult to know what pieces of information are important. I'll kind of talk through them real briefly. So it seems like there's four categories: usual interstitial pneumonia, probable usual interstitial pneumonia, indeterminate for interstitial pneumonia, as well as alternative diagnoses. The main three key features of usual interstitial pneumonia is this honeycombing, reticulation, and traction bronchiectasis. That's going to be the findings that I'm going to be training the data set to see if they're going to be able to identify, because in images that have these appearances, that's going to be usual interstitial pneumonia the majority of the time. It's going to have to learn to rule out UIP when there's more ground glass opacity to make a negative prediction for for ground glass opacity. One thing it's going to have to learn is that there's an importance to this apical basilar gradient. UIP is a disease that pretty much affects the lower and peripheral areas more. So basilar is the lower areas, and then the subpleural is going to be the peripheral areas. It's going to need to recognize basilar, subpleural features of honeycombing, reticulation, and traction bronchiectasis. It's going to have to recognize that when there's pleural plaques, dilated esophagus, any of these, then it's going to be the alternative diagnosis. I'm going to be curious to see the results of the project as it comes about. So, going on to building the skills necessary to do such a project. Well, what I have here is my image detection algorithm that I have written out. So I'm going to first be using this data set, which is the Yale FACES dataset. So the Yale FACES dataset is a publicly available dataset. We can learn more about it right here. So basically, there's 165 grayscale images in GIF format of 15 individuals, and then they have 11 images for each of these subjects. So 11 times 15 is the 165. They have different facial expressions, and then there's also different configurations of light. So in terms of configurations of light, center light, left light, right light, and then they have different facial expressions, so like surprised, wink, happy. This database, you can use it as well. So what I did is I did download all these individuals, and then I stored them in my folder right over here. So here are the faces, and what I did is I want to use image processing technique and detection, but instead of facial expressions, what I want to predict, I chose is the configuration of the light. So I cleaned up the images to only the images that had facial configurations of light, and then I was left with about 45 images. So you can see from here that each of these images, the light is shined on the individual in different ways. For this guy, the light is straight on at him. For him, the light is shining from the left side, so it's casting a shadow to well, it's like on, it's not on an anatomic right, it's on photo left. So his right side, but our left side, the light is on our right side and his left side. So it's casting a shadow on his right side and our left side. So you can see that with all these images. This is going to be an algorithm that I'm going to build that's going to detect what side the light is shining from. So is it going to be right, left, or center? And how do you think the image detection system is going to do that? It's actually pretty basic when you think about it. So essentially what it's going to do is it's going to turn all these images. So I'll open up one of the images. All these images are grayscale, so it'll turn each pixel, it'll go through a lot of pixels and turn them into the shade of gray. From the number is going to be from 0 to 255. So the darker the color, the more points it's going to get. And through training, it's going to recognize that the areas with more dark on our left side, on his right side, that means the light's going to be shining from our right side or his left side. So this light will cast a shadow, and the machine algorithm will determine that the light is coming from the right side. It will do this for all the images. It will convert all these into pixels. So what you'll have is you'll have the rows being 45 individuals, and you'll have the columns of each pixel will be a column, and it will be populated by the shade of gray from 0 to 255. Alright, so now that we have the images, it's time to read it into RStudio. So here's where I saved the image, and then I'm going to set that as my workplace directory. Then I'm going to go through all the files in my library, and I'm going to pull them up. Once I've read in all the files, what I'm going to do is turn the images into the pixel form, and then I'm going to create my matrix data frame, which, as I said before, all the rows are individuals and all the columns are going to be the shades of gray. And once I've done that, I'm going to first do my first statistical technique, which is principal component analysis. The principal component analysis is going to decompose all the values in the shades of gray for each of the individuals, and it's going to break them up into two nice singular vector decompositions or eigenvalues. Once I have that, I'm going to be labeling the images for based upon if the light came from the right, center, or the left. And then I'm going to plot them as well. So after I run this code, what ends up happening is it's going to plot, after I ran this code, it's going to plot each of the individuals, and then it's going to choose the principal components, which are going to basically decompose all of the different pixels and then magically linearize them into two of the most important components. What we see is that the individuals do tend to cluster in three main groups that we've colored: right light, center light, and the left light. So everyone that had a right light, they tend to be more clustered. That means our algorithm has found a way to group them based upon these principal components. Everyone with center light are here, and everyone with the left light are here. And then what we next have is we're going to start running a supervised machine learning model. Above was the PCA, which is the unsupervised, and now we're going to run the supervised approach, which is the random forest model. And how we do that is with the caret package. So let's just run that. And right now what it's doing is it's training a model, and what it's using leave one out cross validation, and it's a k-fold cross validation that makes a test and train data set, and then it tries to evaluate how good our model is. So when we look at the final model, what we have is we have how good it was at predicting based upon, after training from a set, how good it was at predicting the test set. And you can see how good it was for predicting center. It was pretty good. It only had 6% errors. For how good it was at predicting left light, pretty good too. And it seems that it was worst at predicting individuals that had the right light. So after I've pretty much shown a proof of concept for what I could be doing for faces, I'm going to be building the data set for usual interstitial lung disease, trying to figure out if we can build a training set that can predict apical, pleural, apical basal gradients, cephalocaudal gradients, to see and figure out different patterns like bronchiectasis, traction, reticulations, trying to rule out ground glass opacities, and honeycombing, and be able to predict cases of usual interstitial pneumonia from those that don't. Thank you.